Dirac notation and product spaces. Time to get our hands a little dirty and dive into this notation and the language with a great example of inner and outer products. Here we're asked to consider a 3D or three-dimensional vector space spanned by an orthogonal bases of ket1, ket2, ket3. Alright, so here we are a alpha ket vector in blue of I ket1 minus 2 ket2 minus I ket3 and beta as such. Let's go ahead and realize here that spanning in this case means that we live in the vector space, any vector, so long as we have a linear combination of the bases vectors. So the linear algebra is coming through again, and all the other fancy stuff. I'll go ahead and make a post about all the quantities and definitions because I think that'll be helpful. But speaking of definitions, let's go ahead and review what we had with the Bra-Kets. Here we saw that the ket vector was a column vector. Be aware that although this notation is convenient, it hides the dimension of the ket, meaning that we have an n×1 vector. Similarly, the bra, which we transpose into the dual space, is a 1/n vector, a row vector. So be aware that the notation is tidy, but it hides a lot. Alright, so keep that in mind. And here, if we just, look at what we're asking for, we want to construct the bra alpha beta and find the inner product alpha beta and beta alpha and confirm this identity of the conjugate property. And then we can go on and, find all 9 matrix elements of the operator A hat, which is defined as what looks like the ket alpha and the bra beta in this basis system, and then construct the matrix A. Is it Hermitian? So a lot of familiar words and a lot more definitions. Let's go ahead and dive in. So we say here that the bra vectors are actually the dual ket vector, meaning that we live in a dual subspace, which is just taking the transpose and conjugate, all part of being properties of the vector space, which we know we're in due to being a Hilbert space. And then B here, we note that what we're asked for is the inner product. We have a bra and a ket. We know we get out a finite thing, and this goes back to our definition of inner product. Kind of reminds you of the dot product with the vectors. And here we see that we have a 1×1 dimensional entity, so we know we're getting a scalar. So let's go ahead and we will distribute everything from A. We'll just write out A. We used it here, so go ahead and copy it down. Beta we had in the definition. We note that this distributes fine because we are, this distribution is a part of the properties to be a vector space, which we know by default we are due to being a Hilbert space. Okay, so no big deal there. Just distribute out. Be careful. All the ones go. This goes into that and that. This goes into that and that. And this goes into that and that. I'd like to point out here how we have kind of a weird little symmetry here. We have the 1, 2, 3s here, all 1s here, 1, 2, 3 here, all 3s here. This, if you've taken linear algebra, kind of looks like a system where now you can start to see where matrix factorization comes in due to these things, but that's a topic for another day. Let's just realize that the distribution is such, and now we need to simplify. So simplifying, scalars can be moved out of the kets and bras, no big deal, linearity saves us that. But we were also told that this was an orthonormal basis, meaning that we have this condition here where we are 1 if the indices match and 0 if they don't. Clearly here, we see that these indices of 1 and 3 don't match, 2 and 3 don't match, 2, 1, 3, 1, all of them go bye-bye, and we're just left with the matching indices. We like this, and it saves us time, and here's why. You can see the illustrious example of why it doesn't matter whenever we use orthonormality. We don't have to do this kind of distribution and calculation every time. I'm only doing it to highlight the fact that this is where we get the results. Nonetheless, we see that here we get an I, negative I, and I, that gives us negative I squared. And then this here, this inner product gives us 1. Here we're left with a 2 and an I, and then again, inner product gives us 1, so we simplify quite nice. Now, if we switch the beta alpha, we do the same thing. We see that we just need the 1, 1, and 3, 3 components, and that gives us 1, negative 2i, so no big deal. But what we can see is that if we look at beta alpha, we get 1 minus 2i, and if we take, notice that we could take the conjugate of this thing by switching this negative sign to a positive sign, we see that we get indeed the inner product alpha beta in the conjugate. So pretty cool. We like this. Not too bad. What I'd like to note next is that we have this operator which looks like the opposite of the inner product, which of course if we have an inner product, what do you think happens when we switch the order? We create an outer product. And so we have here again, based on the fact that our dimensions are what they are, even in this hidden notation, in the inner product we got a scalar. In the outer product we're going to have an n by n matrix, so we know we're going to have, in this case, since we were a 3D space, n is 3, so we're going to have 9 components to deal with. So just be aware, it gets a little spicy with all this stuff, but these definitions do come in. The notation is nice and simple, but just be aware, there's a lot of hidden stuff there. Alright, so if we distribute just like we did for the inner products, we see that we can simplify this down pretty quickly. You notice that we're going to have a hard time with the 1, 1, 1, 3, all that kind of stuff here, because these are the basis vectors. So what in the world does something like the ket of 1 and bra of 1 represent? Well, of course, let's recall that we spanned a three-dimensional vector space, meaning the ket has 3 components, and hence 2 do the bras. So what we can do is consider an example of what is going to happen. Let's go ahead and look at that. Well, we've seen this before, maybe not in this form, but let's say that the basis vector here is, and that we're orthonormal, so all these have to be normalized to 1. Here we see that the basis vector 1, 0, 0 fits that definition pretty fine. And we could say, well, that's kind of like what x hat was when we just dealt in, the vector notation from like E and M, physics 1 and 2, all that other stuff. So if I take the conjugate transpose, to find the bra, I end up with this. Notice that I have a 3 by 1 and a 1 by 3, so if I take the outer product, I end up with a 1, 0, 0, 0, 0, 0, 0, 0, 0. Well, that's just matrix multiplication. Okay, this is the n by n array. But note how clunky this is, the green thing is, versus how tidy this is. So understand that this means that we're taking and finding the component that match these indices. Okay, so if we wish to, we could explicitly find them using a product or definition exposing these inner and outer products as such. And some authors like doing this because of other matrix properties like the diagonalization and other things that you get from linear algebra. But nonetheless, what we see here is that we just end up with the first component, the third, fourth, sixth, seventh, and ninth. We see that we're missing a whole row of elements, 1, 2, 2, 2, 3, 2. They all equal 0. Why? Well, guess we'll find out soon. So clearly, these basis vectors in the form of the ket bra are acting as projection operators. Recall that real quick. That is the exact definition of it. And what we know about this is it will take another vector, because it has to be applied to a vector by definition. And so what this does is it sends the other vector, it takes the result and sends it in the direction of the ket1, so the first basis vector. And that's what we saw in the green matrix on the last page, where we just had that in the first matrix element in that first position. So pretty cool. We like that. It's pretty clever in my opinion. But again, this is a matrix equation, and I think it's more easily seen writing out the outer product as the multiplication of the vectors in a row and column form. So, again, kind of hidden, but you see when we write it out like this, we have the three elements, again, 3D space, three elements, 3D space. Here, we have a 0 there because we weren't told in the question that we had any component in the second basis direction, so we're fine. And then when we multiply them out, it becomes evident why this column here was 0. Okay, so that's exactly why we had no components of 1, 2, 2, 2, and 3, 2. Again, look at the color scheme here. Look at how the column vector here is a column, 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 and then we have a row vector here which goes column, column, column. This again plays into those factorization techniques that you might run into later. Cough, cough, wink, wink. So be aware. So then finally, we simplify this down into a nice matrix formulation. Pretty easy. I think this way is much quicker. But here we see that if we want to test for if this thing is Hermitian, we need to recall that Hermitian means A dagger equals A, where the dagger means the conjugate transpose. So let's go ahead and test out that theory. A dagger, break it up, transpose it, conjugate, doesn't really matter which one you do first, but you have to do both. Easier to do transpose first just because, that's more of a mental mistake error, I suppose. Here, the transpose simply means that we're switching the rows and the columns. So we take this diagonal and we switch the elements. We do, assume that line's a pivot and rotate it. So our 2i goes to this position. So these two switch. This 2i and this -1 switched. This -4 and this 0 switched. So I tried color coordinating it with the main diagonal here. And then everything else on the anti-diagonals gets switched. And then, of course, just apply the conjugate, switch the signs. And you see that here, nope, that does not equal the original matrix A. So this matrix is not Hermitian. Again, Hermitian has a bunch of properties that are useful, and we'll see with more context why they're useful. So thank you for watching. Until next time, stay curious and happy learning.